Take a look at this image. Historic school workshops were built for a specific type of student and a specific mode of operation. Today, education estates face a strict modern requirement: universal access. In June 2026, the government introduced the Inclusive Education Estates Blueprint, marking a definitive shift in how schools approach special educational needs and disabilities, or SEND. The core objective of this mandate is to end regional disparities in support. The goal is to ensure students with SEND can remain embedded in their local mainstream schools alongside their peers, rather than being outsourced to specialized facilities. To achieve this, the guidance mandates that every secondary school establish an inclusion base. These are dedicated, teacher-led spaces designed to provide targeted support. They act as a bridge back into mainstream classroom life, explicitly prohibited from being used as a disciplinary sanction. Designing for inclusion is a proactive architectural requirement. These standards form the baseline for the physical footprint of every modern education estate. Applying these new mandates becomes significantly complicated in high-hazard, heavily mechanized environments like design and technology or engineering workshops. These spaces are inherently high-sensory. The combination of spinning machinery, loud extraction systems, and concentrated activity creates an environment that easily overwhelms students with sensory processing differences. To audit these complex spaces, the new government guidance recommends a day-in-the-life methodology. This requires school leadership teams to perform structured physical walkthroughs, specifically looking to identify points of friction from the perspective of a student with physical or sensory needs. We are going to reverse engineer a fully compliant design and technology estate by translating the blueprint's 10 core elements directly into physical infrastructure. By mapping these requirements onto a high-risk space, we can see how inclusive design naturally overlaps with general health and safety compliance, rather than compromising it. This schematic shows a top-down view of our baseline DNT workshop and adjoining CAD suite. We will start by building the acoustic and visual layers. Looking closely at the heavy machinery zone, we locate the primary sources of mechanical output, such as the bandsaws and the dust extraction systems. These machines generate significant ambient clutter. For students with sensory processing differences, this persistent, echoing background noise creates immediate distress and disrupts focus. Applying targeted sound-absorbing materials to the walls and ceiling dampens this reverb. It reduces the overall decibel level and isolates the sound to the immediate operating area. Next, we address physical navigation. We can utilize high-contrast yellow lines across the floor plan to establish clear spatial boundaries. While already a common safety practice, extending these markers throughout the entire workshop creates a comprehensive visual zoning system. This allows students to instantly differentiate between active hazard zones where machinery operates and calm, designated transit paths across the room. Managing sound output and visually organizing the floor space allows students to navigate the environment independently and safely without requiring constant verbal direction from staff. This isometric diagram isolates a single workbench and its adjacent machine control panel to illustrate the physical accessibility requirements of the space. A thorough audit must evaluate the distance between the operating position and the interface points, testing the reach to tools and control panels. Every student, regardless of physical mobility or reach radius, must be able to instantly and safely actuate the emergency stop buttons. The workstation itself must also adapt to the user through work surface flexibility. Benches must be designed to adjust their height up and down. This accommodates the specific bodily requirements of the student operating the station. Providing a seated, highly stable option alongside a standing configuration allows students who struggle with physical endurance to participate in complex manufacturing tasks. When the infrastructure physically conforms to the user, the environment no longer dictates a student's pedagogical potential. Moving off the main floor and into the adjacent CAD and 3D printing suite introduces a different set of challenges. Technical drawing and sustained screen work require intense visual focus, creating a unique sensory load for the user. Here, we see how harsh, uniform overhead lighting casts stark shadows. The persistent flicker of fluorescent tubes and the glare reflecting off monitors cause rapid eye strain and sensory fatigue. The guidance recommends dimming the overheads and installing localized, adjustable task lighting at each specific workstation. This modification caters directly to individuals with light sensitivity, while ensuring that the immediate workstation retains the high visibility required for precise modeling. We must also integrate a dedicated quiet space directly within the department footprint. Providing a low-stimulation retreat immediately adjacent to the active studio means a student who becomes overwhelmed by the sensory input does not have to exit the department entirely to regulate themselves. Retaining that physical proximity keeps SEN students connected to their peers and their coursework, directly fulfilling the core mandate of maintaining local belonging. This complete schematic visualizes the fully optimized department, synthesizing acoustics, visual zones, ergonomics, and lighting. True inclusion requires these features to be baked into the baseline spatial design from the start, rather than retrofitted as an afterthought. For heads of department managing resource costing and controlling internal ARC projects, this presents a clear strategic opportunity. The 10 core elements provide an evidence-based framework to justify targeted capital investments to senior leadership and governing bodies. Upgrading dust extraction acoustics or completely rezoning the floor layout directly aligns department spending with these new national inclusion targets. Furthermore, these exact improvements simultaneously strengthen general workshop safety compliance. A safer space for a student with sensory needs is a safer space for everyone, creating a highly efficient, dual-purpose investment. By systematically removing physical friction, the estate infrastructure supports the day-to-day mechanics of inclusion. This physical foundation ensures that safety and independent access are built directly into the floor plan for every student.